Should I just start, or should we give everyone like a couple minutes break?
Maybe 1 minute break would be good.
All right, cool. I will get started with question 1. So let me share my screen. All right, here we go. Cool. So for question 1, I'll actually probably skip over part A and come back to it after doing part B, because the first part of part B is deriving the equation for entropy of mixing, which will help a lot in deriving our equation for part A. So I know we stepped through this a couple of times, but I will very quickly blitz through part I, in which we're basically deriving this equation right here. And this was done in the tutor session last week. I'm pretty sure it was done in lecture 2. So yeah. So we know from earlier that from lecture, and I won't derive this, but the multiplicity of a system that kind of looks like this, going from state A to state B, is given by the number of particles in A plus the number of particles in B factorial over A factorial, B factorial, right? And then we can just plug this into our entropy formula and kind of expand out. So we have S over KB is equal to ln of this stuff. Right. And we can keep going and use Stirling's approximation. So Stirling's prox. And if you just churn out the math, eventually you'll end up with something that looks like this: S over KB NA plus B is equal to negative NA over minus, and then this exact term, but for n sub b. And then you can kind of rewrite this to be x of a, and then the similar term for x sub b. And this we know right here, this denominator right here is Na plus Nb is n total. So the final formula we get is that the entropy S is equal to negative number of total molecules times Kb Xa ln Xa Xb. A nice and pretty succinct formula. All right, so now we can move on to part B. Or part 2, I guess. In part 2, we were told that there's 2 conditions. The energy of molecule A does not depend on their position, so that's one less factor to consider. And then the energy of molecules of B molecules is higher by 2 kilojoules per mole in the left half of the box. So we're asked, what is the change in free energy from going from the unmixed state to the mixed state at 300 Kelvin in kilojoules per mole? So we know that delta U is equal to 1/2 or 0.5. This is a positive value because we're moving in that direction. And the total number of moles, so we have one of A molecule and one a B molecule. So we have 2 total moles. Is equal to N. NKB, this is the constant we'll be using a lot. So we can just calculate that early. That's equal to 2 times R joules. So delta S, I'm going to ignore B. We can do that later. Delta S is equal to -2 times R, 0.5 ln 0.5 plus 0.5 natural log 0.5. And then we can solve this out to get our value of delta S. Yeah. And then after we get some value for this, we have to divide it by the number of moles because we're trying to find the answer in kilojoules per mole. So we take delta S over mole total, which is whatever this value is, we'll call that x over 2. And that's our final answer for part A. All right, so now moving on to part B. I know it's getting a little bit messy, but at equilibrium, what is the relative probability of A to the probability of B? Oh, wait, I think I forgot to do something. Yeah, I didn't calculate the free energy change, my bad. That's what I missed. So now that we have delta S, we can just use the formula we know. Delta A is equal to delta U minus T delta S. Oops. Plug in the values we know in the delta S that we just got, and we'll get delta A. Cool. So now for part 3, at equilibrium, what is the relative probability of state A over state B? So we know P of A for P of B, and this was also derived. This is in the lecture slides. It's equal to E to negative delta A over RT. And we can just plug in our values and we'll get, because we know what R is, we know the temperature is 300, and we just calculated delta A. So we'll get our probability of A over B. And then we can just invert it for probability of B over A. But yeah, cool. So that is question 1, part B. So for part A, the interest of time, I'll kind of just give you a hint on how to do it, but it's very similar to this derivation here. And again, I think you've seen this derivation in lecture. But basically, the trick we want to use is we know that the number of molecules in these systems with a fixed number of molecules is proportional to the volume. So we can represent the number of molecules in A as proportional to some constant, I'll just call it K, A times the volume of A. And then we can use the similar stuff that we did with entropy of mixing down here to simplify, and then applying Stirling's approximation to find the ratio of multiplicities in the system. And then for part 2 of this question, we are just plugging in a value into the equation we derive in part A. And that's that. So I'm a little bit short on time, but I will stick around in chat to answer questions.
All right, I can start on question 2. All right, 1 second. All right, so question 2 is looking at an unfolded protein and a folded protein. And the protein has 100 residues, and the unfolded state each residue in the unfolded state can adopt 3 conformations, and in the folded state, there's only 1 conformation. So the first part of the question is asking for the change in entropy. So we can start by looking at the multiplicities for both the folded and unfolded protein. So that would be the number of conformations per residue to the power of the number of total residues. So for example, for the folded protein, there can only be 1 conformation per residue because there's only 1 unique conformation, which is given. But for the unfolded multiplicity, there's 3 per residue and 100 total residues. So it would be 3 to the power of 100. And now we can look at the entropies. So you can use the following statistical definition of entropy with the natural logarithm of the multiplicities. And so the answer is asking for the change in entropy of between the folded and unfolded in terms of R. So we can use the definition of the molar entropy, which would be R times the natural log of subtracting each entropy, each multiplicity. And you'd see that the change in entropy would be negative as you go from the unfolded to the folded state, because the folded state has less conformations. All right. So part 2 is asking the relative probability of finding each molecule at each state at 300 Kelvin. And we're given that the folded states can have 1 hydrogen bond per residue, and the unfolded state has no hydrogen bonds, and each hydrogen bond contributes 1 kilojoule per mole. So one important thing to note is we're comparing any folded conformation, which is actually only one possible conformation, versus one specific unfolded conformation, which means that there's not really any entropic contribution to this probability difference. So we can just look at the change in energy between the folded and single specific unfolded. And so for the folded, we can separate each energy term, and we'll have the number of residues times the number of H bonds, because each residue will have 1 H bond, and it'll each contribute -1 kilojoules per mole of stabilization energy. Then the unfolded has 0 H bonds, so it won't contribute anything. So we'll see that when you plug in this value, the change in energy will be negative, which will make when you plug it into the Boltzmann factor, it'll say that the probability of the folded state is higher when you're just looking at the energy contribution, because there's no stabilization energy that the unfolded state is contributing. All right, so next question, now it's basically the same question, except now we're considering any unfolded conformation. So now when we calculate the relative probabilities, we have to consider the entropic difference between all possible conformations that each residue in the unfolded protein can take versus the one folded conformation. And we still have to consider the energy too. So we can do this using the free energy. And we can actually just plug in the values that we calculated before. We already found that the energy term from the last part of the question, and we'll see that will make the free energy more negative as we go from unfolded to folded. And then the entropy, we know that the unfolded protein is going to have higher entropy, so that will make the free energy more positive. And by plugging this value into the Boltzmann factor, we'll see whether the change in energy is enough to overcome the unfavorable change in entropy when going from unfolded to folded. And in the next part of the question, it'll tell you that it will be unfavorable to go from unfolded to folded in this model, because the negative entropic contribution of going from unfolded to folded outweighs the favorable contribution of the hydrogen bonds in the folded state. All right. Click back. Do you know which slide? Yeah.
Yeah, it's like number part 2, I think.
Okay, this one?
I think maybe it might have been part 1.
All right.
There was like, yeah, that one. It was the one with the KB.
Okay. Yeah, actually, so for the KB, that would be, you actually, so you don't want it in terms of KB. These are just, so the top entropy would, change in entropy would be per the change in entropy per molecule. But since we want it in multiples of the gas constant R, you can just use this bottom equation only. And then that would be the change in entropy per mole.
Okay, I see. Do we have to multiply with the Avogadro's constant as well?
Well, actually, since you wouldn't have to do that because you'd be, so if you have the Boltzmann constant definition, you'd multiply both sides by the Avogadro's number, and then they would cancel out. So you just have, it would just basically be the same exact thing, except now it's the entropy per mole. So yeah, you can basically just, yeah, use this straight up.
Okay, I see. Thank you.
All right. So yeah, going part 4, we'll find that the protein folding is not favorable under the previous calculation. So it's asking what key component is missing. And so you'll notice that the previous components of the problem just took into consideration the residues of the protein in each state. But one key component missing is the interaction of the protein with the like its surrounding environment, specifically water. And so in the unfolded state, the protein will have a lot of hydrophobic residues obstructing water interacting with itself and basically limiting the degrees of freedom of water hydrogen bonding with itself. And then, so that will be actually a negative contribution for the entropy of water in the unfolded state. So when the protein folds, a lot of those hydrophobic residues are compacted in the hydrophobic core, which actually frees up a lot of the water and increases the degrees of freedom of the water, which is a positive contribution to entropy that would make folding more favorable. So overall, the key component would be the entropy of water that you have to consider. And that's the end of this question. Okay, what's W unfold? So, sorry. So W unfold is basically the multiplicity of the unfolded protein. So it's given that the unfolded protein has 100 residues and each residue can adopt 3 conformations. So basically there's a bunch of different ways that the a bunch of different like states the unfolded protein can exist as. So W unfolded is taking that into consideration, and then that would give the entropy. So it's the multiplicity of the unfolded state, protein specifically, yeah. Does that make sense? Anyone else have any questions? All right, yeah, feel free to message me as well.
All right, so no more questions on number 2. I'll go ahead and move to question 3. All right, can everyone see my screen? All right, so for question 3, you're asked to use the ideal polymer model of a protein as a way of studying protein folding. And just a quick refresher on that, essentially it models each axis of movement for the polymer as a random walk where each residue is considered a segment of length L, and the directions that are allowed to move are either right or left. And based on that, you can measure the total displacement. And of course, the probability of a given net displacement is given by a binomial distribution, which I think you all covered in lecture a couple weeks ago. So question 3 starts by asking you to consider a protein of 10 residues, and notes that the projection of the protein chain on the x-axis is considered to be a random walk of 10 steps, since we're starting with one residue and then we walk for 10 more residues, each with a step length of length L. And they ask what multiplicity is associated with protein conformations, where the distance between the ends, so the end-to-end total displacement, is 2L. So if we let nr be the number of steps we take to the right, and nl be the number of steps we take to the left, we can solve for this by noting first that we have 10 total steps, so we know that nr plus nl must equal 10. And also we know that our total displacement is 2L, and each step takes L in displacement. So if we assume this displacement is to the right just for convenience, we can write that nr minus nl equals 2, since the total displacement is just given by the number of steps we take to the right minus the steps we take back to the left. So these should be relatively straightforward to solve for nr and nl. And once you have that, we know that the multiplicity associated with the protein conformations is just the number of possible conformations, where you take 10 steps, of which some nr number is to the right and nl to the left. And this is given by 10 choose nr, which should be equal to 10 choose nl. For part 2 of the question, you're asked for what the distance between the ends of the chain is that correspond to maximum entropy and the associated multiplicity. So one thing to note here to start off with is that if we're asked to maximize entropy, we know this is the same as the state with the maximum multiplicity, because we know that entropy increases alongside multiplicity, if we remember the equation for that, in terms of molar entropy. Since ln is monotonically increasing, we know that as the multiplicity increases, the entropy should increase also. In other words, the distance between the chain that we want here is the distance that corresponds to the greatest number of conformations possible. And we know that there are 10 steps total. So we can set up again that nr plus nl must equal 10. And then intuitively, we might guess that the state with the maximum multiplicity is the state where nr and nl are the same. And we know this is to be true because if we remember, the probability of a given net displacement is given by the binomial distribution. And we know that the binomial distribution is symmetric about the midpoint. So we know then that nr must equal nl, and this should give us the answer pretty quickly. And then from there, we still calculate multiplicity the exact same way, 10 choose nr, which, just as a refresher, is 10 over nr factorial, 10 minus nr factorial. And this 10 minus nr quantity is just nl. All right, and for the last part of the problem, it's noted that when the number of residues is large, the binomial distribution is approximated by a Gaussian distribution, and you're given the three-dimensional function for the Gaussian distribution over here. And this probability is proportional to the multiplicity of the chain, where the end-to-end distance is capital L over here. So essentially, given your two constants, the number of residues and the step length of each residue, you have a function in terms of the total displacement. And you're given that a 100 residue protein is stretched from 100 angstroms to 1,000 angstroms. So the first part of this question asks if you expect the entropy to increase or decrease. And again, since we know that the entropy is proportional to the multiplicity, we have to ask, how does W change when we do this? So you'll note that then when there's a smaller displacement, you'll have more configurations possible. And as you stretch the protein out, it restricts the number of different configurations that the protein can adopt as it gets closer to the full length of the protein chain. So based on that, you should be able to answer the first part. For the second part, you have to show that the magnitude of change in entropy for this process is this number given here. And note that this is given in terms of R. So we're going to be using the molar definition of entropy again. Suggest again that entropy is equal to R times natural log of multiplicity. So for the multiplicity, it's given that the probability function is proportional to the multiplicity of the chain. So if this is proportional to W, then we know that all of this is just a constant term. So we can just write that W is equal to some constant k times the probability, is some constant k times probability as a function of L. And we can rewrite that further as just by ignoring all the constant terms, we get that W is equal to some constant, I'll call it k again, just for sake of convenience, times e to the, this term up here, negative L squared over 2n lowercase l squared. So from here, we know that since our entropy is R times ln of W, we know that this is R times the ln of ke to the negative L squared over 2nL plus R times k ln of, erase that, plus R times ln of k. Wait, no, sorry, my bad. It's just equal to this, which we then expand out using the rules for natural log. So we get, this is R ln of k plus R times this expression up here, negative L squared over 2nL. Since natural log of e to the quantity is just that quantity. So we know then that the change in entropy from 100 angstroms to 1000 angstroms, let's just call this L1 and L2 for convenience. This is equal to since the constant term should cancel out when we subtract, this is just R, negative R over 2nL times L1 squared minus L2 squared. And from here, you should just be able to plug in values to get the final magnitude that they're asking for. Are there any questions on that?
For part 1, could you quickly explain how to get NR and NL?
Right. So we're letting NR be the number of steps taken to the right, and NL be the number of steps taken to the left. And we know two things about this already. The first thing we know is that the total random walk has 10 steps. So NR plus NL must equal 10, since there are 10 total steps. And we know that the total displacement is 2L. And since each step has length L, that means the total displacement, the total number of, the total net number of steps taken is 2. So if we assume this displacement is to the right, NR minus NL must equal 2. And from there, you just solve this system for NR and NL.
So does it not matter? Oh, okay. Yeah, I see. Thank you.
Sure. Any other questions?
So the multiplicity for part 1 is equal to the multiplicity of part 2.
Sorry, could you repeat that? I didn't quite catch that.
The multiplicity of part 1 is equal to the multiplicity of part 2.
No. So the NR and the NR values you get for part 1 and 2 should be different. It's just that you calculate multiplicity the same way.
Okay.
Yeah, because in this first one we have that NR minus NL must equal 2, whereas in the second one we have that NR and NL must be equal because of the symmetry of it.
Okay.
All right, any more questions? All right, feel free to ask any more in chat.
Okay, I'll be covering question 4. Can everybody hear me clear? I assume that's yes. Okay, so this question is basically a continuation of the previous question. We're still considering the same ideal polymer, and we're trying to calculate the free energy change, stretching from 100 Angstrom to 1000 Angstrom. So I feel like it's a quite straightforward question. So I want to do a little quick review on free energy for you all. So remember that we have 2 types of free energy equation that we're using in this class. The first one is the Gibbs free energy, and the second one is Helmholtz free energy. So these two has different assumptions. The first one assumes that dP, which is the change in pressure, is 0, and dt is 0, right? And for Helmholtz free energy, we're assuming that dV is 0, and same for T, dt is 0. So I'm just going to do a quick derivation here for you all to kind of let you know why this is the case. So as you can see, the difference in the equation is one is H, the other one's U. So from chapter 6, you have learned that H system is equals to the energy of the system, U system, plus P V system, right? And therefore, for a infinitesimal change of H system, if you take DH system, that will be DU system plus PdV system plus V system dP, right? And because in the first condition for Gibbs free energy, we're assuming that dP is 0. So as you can see, there's a dP right here, right? So this term would cancel out. So this is our final equation for dH. And we also know ds surrounding is equals to negative 1 over T du system, right? Minus P over T dV system. So these two equations, as you can see, they look quite similar. The only difference between them is a term of minus 1 over T. So what I'm going to do is I'll time this side, the right side and left side of the equation, both by 1 over T, minus 1 over T. So what we're getting is minus 1 over T dH system is equal to 1 over T minus 1 over T du system plus, minus P over T now, because we're timing 1 over T, right, minus that, dV system. So now we get these two equations. As you can see, the left side now are all the same. So we can conclude that S surrounding is equal to negative 1 over T dH system, right? So this is the first equation we got. I also want to remind you that we define a spontaneous change as the total entropy is greater than or equal to 0, right? But we can write the total entropy as the entropy of the surrounding, ds surrounding, plus the change in entropy of your system, right? And this will be greater or equal than 0. And then as you can see with these two equations, we got a term d as surrounding right here. So we can change this term with this equation. Okay, so with these two equations, what you get is ds system minus 1 over T, right? HS system must be greater or equal to 0 when it is a spontaneous change, because of course you can write as total is equal to this, but we are just ignoring that term right now. Okay, and this is why we define Gibbs free energy as G equals to H minus TS. Okay, and then if we take dG equals to dH minus SDT, minus TDS. Since we have an assumption right here, dt equals to 0, this term will be 0. So the change in Gibbs free energy will be dH minus TDS. Okay, but in this question, this one is not very useful. That's why we're going to also derive the other one. So in this assumption, we are looking at a system with volume equals to 0. So the usefulness of this equation is that when you're not considering, for example, gas expansion or a lot of gas molecules changing volume, then this Helmholtz free energy equation will be very useful for you to calculate free energy. So you can find this equation on your textbook. It's equation 9.8, where for a system, the energy can be described as du equals to the partial derivative du ds under constant volume and number of molecules ds. So this has to do with what? The entropy of the system plus, so this is the entropy term, plus the partial derivative du dv under constant s and n v. This is the volume term. And partial derivative du dn under constant volume and entropy dn. So this one is the number of molecule term. So if dv is 0, with equation 9.15, ds surrounding equals to negative 1 over t du system minus p over t dv system equals to negative 1 over t du system. So as you can see, this one looks really similar, this equation, to this equation that we came up with. And that's why if you combine this equation with the total entropy, which is equal to surrounding plus the system greater or equal to 0, you will get d system, d s system minus 1 over t du system greater or equal to 0. Therefore, for a spontaneous change, you want du system minus TDS greater, smaller or equal to 0. And that is why we define free energy A equal to U minus TS. Right? And the same thing happens here. If we want to see the change in free energy A, it will be du minus S dt minus TDS. And because we have the same assumption, dt equals to 0, so this term would cancel out, and this will be our final equation, minus t ds. So this one is a very useful equation to use in our question here, because the assumption here, if we reiterate, the first one, of course, dt equals 0, and more important one, dv is 0, because we're just considering a protein, one protein molecule doing random walk, right? So it's a very small entity, and the volume doesn't really change. So after all the derivation for part 1, what we're going to do is we're going to use delta A equals to delta U minus T delta S. And delta U here is 0, right? There's no change in the energy of the polymer. And delta S is basically the number you calculate from the previous question, the last part of the previous question. So what you want to do is you want to just plug that in, and you know T is 300 Kelvin, and you will be able to calculate the final answer right here. And the second question, question 2, we're looking at how many ATP molecules we need to use if we're assuming this condition. So what you want to do is we will use delta A. Okay, so let me rewrite this. Number of ATP molecule is equal to delta A, which is the number you calculate right here, divided by the energy absorbed by your polymer, 35 kilojoules per mole per ATP molecule, right? And as you know, delta A is going to be in kilojoules per mole. So the final answer that you get should be a positive number, first of all. You don't need negative number of ATP. You need a positive number of ATP. And that would be this many number of ATP, because kilojoules per mole would cancel each other. Okay? And for the second question, I can tell you that you're actually getting a smaller number than 100 ATP. There are several reasons that can contribute to this. The first thing is that the model we're using is a very simplistic model, and the discrepancy can come from we're using only an approximation to calculate the number of ATP. That's the first reason. The second reason is a lot of the energetic stabilization of the protein polymer is being ignored. That's why you might need to use more ATP. You'll have to use more energy in order to stretch the protein. Okay, we're only considering in this question, as you can see, there's no change in the delta U, right? It's because of that we need less ATP. If this term is not 0, then we would need to use more ATP. Okay, so this is question 4. Feel free to ask questions if you have any.
Sorry, could you repeat what you said for the last part? It's because we didn't consider the protein.
So yeah, I can talk a little bit more about that. So first of all, in the question, we assume that we're only looking at you see there's no energy change associated with the conformational changes. That means, right, delta U is 0. We agree with that piece of information. And therefore, we're only considering the change in entropy of this protein polymer. Okay, so if we are taking consideration of delta U, which means now let's think about it. What if delta U doesn't equal 0? There are stabilization energy that's holding the protein to prevent it from being stretched longer. Then adding that number in our free energy calculation equation, that will make it larger, right? And therefore we need more ATP. Does that make sense?
Yeah, that makes sense. Thank you.
Awesome. So again, in this question, the only thing we're considering is the change in entropy, which is disorder, right? The change in disorder, not energy. Okay. So basically, we're saying like, if you stretch the protein longer, are you decreasing or increasing the entropy? Of course, our answer is you're decreasing the entropy, which is not good. You're limiting the ability for this protein polymer to have more conformations, which the protein doesn't like. Okay, yeah, so that's the idea of the question, but we're not considering the energetic term, delta U. It is 0, okay? All right, are there any other questions? Okay, if there's no question, that's question 4 for you all. And if you're wondering, you want to dig a little bit more into the derivation of these two free energy equations, you can go to your textbook, the Molecule of Life, 9.3 and 9.4. Okay, there are more detailed steps in there. And feel free to come to tomorrow's session if you have a specific question about it. Thank you very much.